It's my pleasure to introduce an august set of speakers for you today. But given where the hydrogen ecosystem is in India today, I think for the last 3-4 years we've seen that growth from strategy to implementation, and now a lot of use cases focused on end use. Today we'll cover a few that are focused on the steel sector, that are focused on the refinery sector, and I think we have an eminent set of panelists to take you through it. Our first speaker for today is Naveen Alawat, who heads Power2X at Jindal Steel, and he's going to talk us through the imperatives for green steel and how they are sort of relevant to the Indian context. Naveen, over.
So, good afternoon, ladies and gentlemen, and thanks for IEW for giving me a chance to really update you what exactly green steel is. Everybody is talking about low carbon emission green steel world over, and there is so much of traction that is happening because of the low carbon intensity and the renewed business of what green steel coming under hard to abate sector. So I will talk about the imperative, why it is important, why people are so interested, why this actually makes sense, important sense, business sense to really take off. So I think the first slide is pretty clear. We all are aware that where exactly we are going in terms of the global temperature, with the kind of actions, the talk and the action that is there. I think there is a huge mismatch. You can see from the current curve that with the current pace, we are not going to meet the commitment that have been taken in Paris. So even if we really push it, so with the current trajectory, we are not going to meet. Even with the new announcement, we are way off. So we have to really push our actions, and we have to sort of act accordingly to ensure that we actually fall near to it. Anyway, we are going to miss it by a big chance, but at least there will be I think with the activities and the actions, there is a good chance that we will be able to try to bridge the gap. And it is not about the climate alone. There is also on the right hand side, if you see, there is a correlation between the GDP and the temperature. So with a high temperature, you can clearly see the impact on the GDP. So we all will be impacted. Of course, the future generation is going to be impacted in terms of the clean air, in terms of the overall climate activities, floods, and so many things that is happening. Delhi is a classic example where we haven't seen a clean air for last 3-4 months, actually, right? So, but apart from that, you also have an impact GDP as well. The businesses are going to suffer. There will be, so that's why this green steel and the low carbon products, whenever you talk about the molecules, the electrons, it will have an impact on the business case as well. So now, zooming into steel, what exactly steel represent? You see on the left hand side, 0.7%. This is the steel contribution to the GDP, global GDP, right? The carbon next curve is about the impact the steel is going to have. So 0.7% is the contribution to GDP, but the emission is whopping 7%, right? In the overall global GHG emission that we talk about. And right hand side actually tells us that why steel, aluminium and cement, it is falling under hard to abate. Now why hard to abate? 70% of the global steel manufacturing, it is happening through the BF blast furnace / the basic oxygen furnace route, right? 72%. And that corresponds to 95% of the emission that is happening corresponding to steel. Now steel, if we talk about globally, we are emitting 3 gigatons of CO2, 3 gigaton. Then comes the DRI electric arc furnace route that forms 3% of the emissions, but only 6% on the capacity side. Then the electric arc, then the scrap based electric arc furnace route, 22% of the production correspond to 2% of the emissions. So that's why the hard to abate 70% is where the manufacturing is happening, the emission is 95%, and we have to zoom in to this part of it, which is slightly tough. It is not easy, it is not difficult, but it is slightly tough because the levers are quite restricted, the levers are quite less, and that is, we have to play among those levers to start reducing or accelerating the decarbonization. Now, these are the levers that are available today. So you talk about the existing processes. In the existing processes, what we can bring in. Circularity is absolutely the quick win, efficiency and renewable power. So these are the three things which are in our hand where we can really accelerate, and we are accelerating as a steel industry as a whole, but these are the levers that we already have in our hand. Then the new processes or the 2B processes, adoption of low carbon hydrogen, the carbon capture utilization, and the fuel switch, right? Coming to the existing processes, circularity is where our focus is right now as a company and plus the industry as a whole, where all the converting the waste to wealth, all the co-products, all the byproducts coming out from the plant. Slag is one of the classic example where the BF slag that is coming out, we are using that slag to make to use in cement industry, right? All the fuels that are coming from our processes like gasification oil, the tar that we are using within our existing facility or assets to replace it with LDO or HFO. Renew efficiency, adoption of the variable frequency drive is one of the factors that we are doing. Adoption of the ML, AI, where the idea of efficiency is about how we can consume low and produce more. That is actually the overall bottom line on the efficiency side. Renewable power, I think India is a mature market now. Solar is quite mature. Wind is also now actually coming to that point. So with the adoption of renewable energy, there will be an incremental capex that we have to sort of bear, but it will have a 15 to 20% impact on the overall carbon intensity. So these to us, I think are quick wins, quick levers that we have, low-hanging fruits, where we have done the calculation that with incremental 10 to 15% of the capex, we'll be able to reduce our carbon intensity by 25 to 30%. Then comes the low carbon hydrogen. Hydrogen is everybody's talking about this is going to be a silver bullet. Yes, it is, but with the current, I think the levelized cost of energy that we have, close to 3.5 to 4 odd rupees round the clock, because our processes require round the clock. It is not that daytime we use hydrogen and in the night we sort of run on a high, basically high carbon intensity or use fossil fuels, right? So round the clock carbon capture utilization is again a lever that we have from medium to long term. And fuel switch is definitely, I think, the uses of ethanol, making methanol, that is actually will start falling into the circularity. So the CO2, the captured CO2 that we have in our plant can be valorized to make ethanol, and that ethanol can be used as a blending media, can be used within our steel complex. So again, you can see the action happening across the value chain. This is super important. There is no silver bullet, my friends. We have to start evaluating all the possible pathways. There is no silver bullet. If someone will say hydrogen is going to come and eliminate all the pains of any hard-to-abate industry, it is not. So we have to play across the value chain, starting from we always say mines to metal play. So if you come to upstream side, input material like mining, shipping, we have to start embracing mining, deployment of the electrical trucks, that we have already started EV trucks at our mines, the green methanol on the shipping, starting with blue methanol, and then coming to the main steel making, iron making side, where the deployment of renewable energy, the biosyn gas, the bio coal or biochar, carbon capture utilization, and on the downstream side, again on the shipping side. So you see a interplay of all the possible pathways or the levers that we are deploying to reduce our carbon intensity. Now, hydrogen is a key ingredient, but you see the possible challenges or the pain points across the value chain. Power generation, we have to take care of the intermittency. We have to, bear with the capacity utilization factor, and then how you optimize this interplay, the hybrid part of it, right? The wake losses that is happening in the wind power, how we sort of optimize the overall configuration, how we ensure, because as I said, whether you talk about electrons or molecules for the steel plant, we need round the clock availability of these things, right? So that is where it is super important that we need to have greater than equal to 90% availability. Then the electrical infrastructure, again energy storage, in the daytime when there will be so massive curtailment, how we can use that energy to use as a storage, or oversizing our electrolyzer to store that hydrogen during the daytime and use it in the night time. So that optimization is also important. On the long duration energy storage, now with solar and wind, we can only hit 14-15 hours a day, right? Then what about the remaining 9 to 10 hours? So we definitely have to deploy the long duration energy storage. Batteries is one of the 2-3 hours it can take, but what about the others? Thermal energy storage is one, CO2 air batteries is the second one. So that is also need to be evaluated. clipped electricity or the curtailment that is going to happen during the daytime, how we can use this clipped electricity or curtailment in our steel operation. So it is all about synchronization, because all these value additions are going to have an impact on the levelized cost of hydrogen or delivered price of the hydrogen. Then the third part about the electrolyzer, I think that is also important in terms of the which technology to choose. Alkaline to PEM, pressurized alkaline, solid oxide, which one will give the most upside, how we can integrate. SOEC, we have found out alkaline, though it is mature and easy to take off as a short term, but SOEC we believe can be integrated with plants like us, steel, nuclear, refineries can be integrated with the plant to use the low temperature and the high temperature calorie heat to make steam, and that steam can be used as the input material to SOEC. Then about the use of the byproducts. Now, when we use electrolyzer, for every liter or every kg of water that we use, 9 kgs of the water that we use to make 1 kg of hydrogen, 8 kgs of oxygen is going to come out. So what we'll do? Now, luckily for steel plant, we use oxygen for our DRI operations and for electric arc operations. So we can valorize this oxygen to use in our operation. That will have an impact on the overall levelized cost of hydrogen. So all this integration is super important. Hydrogen downstream storage is important because, as I said, we have to take care of the hydrogen round the clock. We have to store in the liquid form, in the LCOH form, in the pressurized form. So all sort of in caverns, we have to basically evaluate all possible hydrogen storages basically that is possible, because we need storage. Second, about the steel technology choices, that is also super important. The product quality, what is the percentage carbon that we have to maintain, right? So depending upon our customer requirement, we have to also optimize the overall technology. But the good thing is that there is a technology that is possible, the technology that can work with 80 to 90% of the hydrogen, it is already available. Now you see here, these are some of the pain points that I have told you, but there is also the upside. There is also the action that is happening across the value chain where we are optimizing it. It is not that by seeing those challenges we are not working. There are solutions to those challenges as well. The first is about the green hydrogen, low carbon hydrogen. I think the partnership is super critical here. There has to be more collaboration that will happen. Now for us, our heart beats for steel. We know how to make steel and sell steel, right? So now hydrogen, if someone is willing to give hydrogen, over the fence hydrogen, it will definitely make sense for us. So we don't have to focus on that part of the business, right? So that is the collaboration in partnership is important. Availability of the high grade pellets. This is super important. If we have to make DRI or low carbon emission DRI or steel, we need high grade iron ore or pellets. Now in India, if we zoom into India, we have got close to 1.5 odd billion tons of reserves. But then apart from those reserves, the iron grade, it is at a lower level, 58, 59, 60%. So we have to beneficiate that iron ore, or we have to also think about importing low, basically high grade iron ore or directly HBI or DRI. So we have to think about in those lines as well. The last part is also very important about the DRI and electric arc furnaces construction time. Because everybody is jumping, all the steel makers, they have to, considering CBAM as one of the potential opportunity, everybody is jumping to go for this future ready technology, hydrogen based DRI electric arc furnace. But the technology partners are quite restricted. It is not that we have got plethora of technology partners, quite restricted, only 2, 3. So there will be huge bunching issues that are going to happen. So partnership with these technology partners, historical partnership with these guys are definitely going to make impact, plus your relationship with the EPC partners, right? So that is also important, because we have seen based on our experience that how you deal with your EPC partners, how you deal with your technology partner will make a huge impact on the commissioning time and the construction commissioning time of the project. Now, friends, this is the opportunity. Why everybody is thinking about going for low carbon emission green steel. You see, by 2030, Europe is really leading the change in terms of the certification, in terms of the policy, in terms of the definition of the low carbon emission green steel. This is where the opportunity is. So as per this chart, you see by 2030, overall requirement or demand of low carbon emission steel in Europe will be close to 100 million tons. Close to 100 million tons, right? We take the most pessimistic scenario as a 50 million ton, absolutely 50% strike rate. Now, if we take all the announced capacities in Europe, H2 green steel, from ThyssenKrupp, from Salzgitter, from SSAB, they won't be able to hit beyond 10 to 15 million ton. So 35 million ton, there is absolutely a base case demand that is going to happen, and Middle East and India can definitely grab this opportunity, and especially the Indian steel makers, though our carbon intensity remains high, but I think the kind of levers that we have, we are blessed with the lowest, one of the possible lowest levelized cost of energy in India. So that is going to be the key driver where we can reduce the levelized cost of hydrogen and start adopting that hydrogen. So this is the one of the demand that one of the trigger, one of the most motivational, inspirational thing that is there in front of us. Now, second most important thing, that from the demand side, how it is going to create, accelerate the demand side. This is also important. Now, customers like you and us, who are the final consumers, we want to buy a car made from low carbon emission or green steel. So car has 1 ton of steel, right? So now, if you take the lifetime emissions of CO2 from from a car, it emits close to 12 tons of CO2, 12 tons. Now 1 ton of steel emits 2.5 tons. So 2.5 tons correspond to steel, 3.5 tons correspond to aluminium, and remaining 6 to 7 odd tons of emission will come from plastic and batteries. Now the automakers, they realize that out of these three factors, the low hanging fruit for them is of course steel, because aluminium very difficult to crack. You need huge amount of energy, renewable electrons round the clock, very difficult. Plastic, and same is a case for batteries. So that's why there is a huge demand from the automakers. They have to commit, they have to complete their pledges, they have to complete their commitment by 2030, 2035, 2040, because steel forms 85% of their scope 3 emissions, and they want to reduce it, right? So you see the motivation here. The end consumer like you and us, who have to buy a car, the final impact, if you are buying a car of 30,000 euros, the incremental capex which you have to give, we have to give from our pocket, is 300 euros only, which forms less than 1%. Close to 4% in in case of appliance. You buy a washing machine or a fridge made from low carbon emission steel, the impact is only 12 to 15 euros, which is like close to 4%. So a study was done by Boston Consulting Group before COVID. So it was a very comprehensive survey where they sent the questionnaire to all the possible consumers, that are you willing to pay a premium if you buy basically a product made from green steel or low carbon emission steel? Only 10% responded that we are not willing to give any premium. The same study was done post-COVID around 3 years back, and a whopping 80% of the consumers, they said that yes, we are willing to pay a premium if we have to really leave a legacy, sustainable legacy for our upcoming generation. So this is also one of the important case wherein the demand is being triggered from the automotive and the FMCG or the white or the yellow good suppliers, followed by wind. Wind is also a classic case. Now, we are now requesting wind guys that you are motivating us to go from black electrons to green electrons, right? We are also embracing that, solar, wind, we are doing it. But then you also have to change. You cannot keep on using grey steel for a wind tower. So there is also a circularity that is also motivating, and all the wind tower manufacturers, they are also coming up to start sourcing at least 5 to 7 odd percent low carbon emission green steel. So this is one of the project that we have doing, one of the world largest green hydrogen ready steel plant in Duqm in Oman, our sister company, and 2 phases, 2.5 million ton each. The first battery is going to be commissioned by FY 26-27, and within a gap of 1 year, the second battery is going to come. Now you see here the transition I was talking about. So the current product PCF is product carbon footprint, the embedded carbon that is there in the steel. So the journey will be from 1.8 tons of CO2 per ton of steel to 643 CO2 per ton of steel. You see with the help of these levers, how we will be aiming to reduce the carbon intensity in the product. Now, depending upon the requirement from the customer, it can be even brought down to further lower than 643, depending upon the willingness to pay, depending upon the carbon price that is there in the market. These are two super important things that will drive the overall acceleration and also the demand. So, friends, it is not going to be a walk in the park, but however, we are prepared. I think the entire fraternity, we are prepared. We are being already labeled as hard to abate, but I think the kind of, especially in India, I can tell you that the kind of knowledge, the kind of commitment that we all are possessing, I think it will be a great opportunity for all of us to really tap the demand that is coming out from Europe. So thank you so much for giving this opportunity and for your patience. Happy to take any questions after the presentation. Thank you so much.
Thank you so much for that, Naveen. I think it was a good exposition of the entire green steel ecosystem. And I think the point you said about whether it's a silver bullet or a Swiss Army knife is something that only time will tell. I think I liked your point on partnerships, and that's where on technology and partnerships that will pick up the next presentation. So we have a group of technologists from KBR, Rajesh Shindar and Amit Parekh, for presenting to us on ammonia cracking technologies. Please.
Good afternoon, one and all present out here, and thank you India Energy Week for having this event where all the brightest minds from India and globe are discussing our future of energy. And thank you again for inviting me to be part of this conversation. Today we will be discussing the last missing piece of jigsaw puzzle when we are discussing clean energy scenario in terms of hydrogen economy, and that is ammonia cracking. I'll invite my colleague Amit to introduce ammonia cracking and KBR in general. Thank you.
Thank you everyone. Good afternoon and thank you Rajesh. So before starting the presentation, I would like to quickly go through introduction of KBR. So KBR is a technology company. We provide solutions for science, engineering and technology to governments and companies across the world. We have presence of around 80 plus countries, and under sustainable technology business vertical, we are providing around 85 plus technology licenses to in refining green ammonia, olefin, chemical and critical mineral portfolio. So journey toward net zero, and as we all are discussing in various presentation in this session, that climate change is one of the biggest challenge for mankind in present and in future, and use of hydrogen as a clean fuel is one of the solution to mitigate this issue. Now if we look at data, hydrogen is called the fuel of future, and if we look at the hydrogen demand data, so by 2050 it is expected or estimated that around 600 million ton of hydrogen demand will be there, and out of that around 2/3 of hydrogen will be contributed from the green hydrogen. But this demand also very closely associated with temperature target and use of other technologies like methanol, electrification and carbon capture and storage. Same way for India, the projection is that by 2050 demand of hydrogen will be around 30 million ton, and out of that 90% of hydrogen will be green hydrogen. India can be, if utilized, India can be net exporter of green hydrogen, as well as India can be greatly benefited by saving around 250 to 350 billion USD in energy import bill over the next 3 decades by use of green hydrogen and hydrogen as a fuel. Sorry, I will go back to previous slide. Now challenge with the use of hydrogen as a fuel is that many of the time the production site, green hydrogen production sites are very away from the end consumer, and with hydrogen storage and transportation is a very critical part, and because of the challenges associated with storage and transportation of hydrogen, which is not very energy efficient, it is one of the very big challenge overall we are facing to tap this opportunity to use hydrogen as a say a clean fuel. Now alternative is that use of ammonia as an energy carrier or hydrogen carrier to transport hydrogen from the production site to the end user. Why ammonia? Ammonia has very high hydrogen density, And other associated benefits to use ammonia is that ammonia is being used conventionally in fertilizer and chemical sector, and we already have established storage and infrastructure to transport ammonia from say production unit to end user. So we can utilize existing facility to use ammonia as a carrier, and at the end user site we can use ammonia cracking unit to generate hydrogen. So briefly about existing ammonia cracking technology, which are very limited to small scale units. Mostly these units are very energy efficient and focused on the localized demand, but the need is that we need to have world class large scale ammonia cracking facility, which is energy efficient, low cost production unit. And the major challenge for this type of new technology is to produce ammonia at very efficient, energy efficient way. And operation of this unit should be at higher pressure and lower temperature. And there this, the technology and catalyst will play a very effective and efficient role to achieve this target. So my colleague Rajesh will take through the KBR ammonia cracking technology, which is branded as H2X technology. Rajesh, over to you. Thank you.
So as Amit mentioned, ammonia cracking as such is not a new technology. It has been happening for over decades now, but those technology was very small scale and not very energy efficient. And since we know that making of ammonia synthesis process, which runs at very high pressure and temperature, is very energy intensive. And then we have to crack that ammonia, which is an endothermic process. Again, lots of energy. So we do not have much margin of error in the process to lose energy. So for that, we at KBR we have our ammonia cracking technology as S2X. So as we say, it's market new, but there is a new market for ammonia cracking, but the technology is very reliable because it is based on the legacy ammonia technology of KBR. So whenever you hear ammonia in terms of licensor, more than half of the plant in the world are licensed by KBR. So you already associate KBR with that, and that is not the only jewel in the crown of KBR. I will mention few more. For example, world's largest plant currently running is licensed by KBR. World's most efficient plant running is by KBR, and world's most reliable plant running is by KBR, which ran continuously for 2,162 days consecutively, which is around 6 years. So based on that technology, we already have a ammonia cracking technology where we can license a unit from 10 TPD to 1,200 TPD per day capacity of that can produce hydrogen to that limit, and that can roughly crack ammonia of 10,000 TPD, which if I say in terms of already running plant, that will be highest running plant of 3 size. So, so to crack the ammonia, first step is having the ammonia. And KBR have technology for ammonia also. Since we are talking about clean energy, it is only understood that it should come either from green ammonia or blue ammonia. However, ammonia cracking technology as such does not differentiate in the color of ammonia. So KBR already have a green ammonia technology, which is as K green, and also for blue ammonia technology, Purifier Plus and Purifier A. We also have Pure M, where we produce e-methanol that can also be cracked in hydrogen, but that's a different story. So for ammonia cracking technology, 3 basic parameters that we are going to discuss, 3 important sections. First one is catalyst, second is reactor design, and then flow scheme. So we'll cover those one by one. So as I mentioned earlier, that KBR cracking technology, it is based on legacy ammonia technology. So if we go through the flow scheme, there is liquid ammonia which is vaporized, then we crack the ammonia, then ammonia recovery, then product purification, and then product compressed to hydrogen for the supply. So all of these parts, KBR has already been producing all single unit for years. So for a new technology, we are combining that and making a new technology for ammonia cracking. And I would like to mention that if we talk in terms of hydrogen yield, H2 Act can provide yield close to 80, and if we talk in terms of efficiency, we can provide efficiency up to 90%. So if you are familiar with ammonia, I know you can already recognize those as SMR primary reformer reactors. So ammonia cracking is similarly fired heater reactor. So we have already expertise on these fired heaters. Other important part is, of course, catalyst. So before going to the catalyst, I would like to cover briefly the ammonia cracking process. So there are 2 molecules of ammonia that crack into nitrogen and 3 molecules of hydrogen, and which requires 46 kilojoule of energy for each mole of ammonia cracking. So that is very endothermic process which required energy. So roughly speaking, that takes around 12% of ammonia itself to provide that required energy for the reaction. So at H2 Act, we do this ammonia cracking in 2 steps. First one is adiabatic reactor, second one is isothermal reactor. Before explaining them, I'll go back to the catalyst part. So ammonia cracking is reverse of Haber-Bosch process, which we already have for ammonia synthesis. So it was but obvious when we were looking for a very efficient catalyst, we went back to the typical Haber-Bosch process catalyst, iron and ruthenium, and also nickel, which has been used for high temperature ammonia cracking. So all these 3 metals were explored for ammonia cracking catalyst, but researchers all over the world actually scanned through the whole periodic table. If you see all those orange metals, they can be active metals for ammonia cracking, and those green metals can be sport, and the blue metals can be promoter. Out of those, KBR's approach is KBR work with all the catalyst technology provider of the world, and we keep a very agnostic process to find out whichever catalyst suits the most to our technology for highest efficiency. So as I mentioned earlier, ammonia cracking happens in 2 parts, adiabatic cracker and ammonia cracker, which is also known as isothermal cracker. So since it is an endothermic process, at adiabatic reactor, we do not provide any external heat. So it starts at 650, in the range of 650, and because of the required energy for the process, the temperature comes down to in the range of 350, and it runs around 20 to 40 bar pressure range. So for this process, since it goes down to in the range of 350 to 400 degree, it is very important that catalyst is very highly active at lower temperature also. So, KBR has option of both nickel and ruthenium based catalyst for this step. And the second one is ammonia cracking, that is also known as isothermal cracking, because it's a fired heater reactor similar to SMR primary reformer. So there it usually operates in the range of 680 to 720 degrees Celsius. So for here, along with activity, it is very important. It has very good mass transfer parameters, very high mechanical stability, and very high heat transfer, because it is a fired heater reactor. So as I mentioned in previous slide also, currently at commercial scale, there are 2 prime candidates for ammonia cracking catalyst. And the picture might say that it's weighing towards nickel catalyst, but it's completely depend on the project and availability of resources. Ruthenium has a very high activity at lower temperature, but as its price can be fluctuating because of its scarce availability. And whereas nitrogen has a reasonably good activity and It's a well-established catalyst for ammonia synthesis process, where primary reformer methynator, we already have been using nickel catalyst for years and years. So that reliability comes along with nickel. So when we have to choose the catalyst for the technology, we took a very elaborated approach. So I have just briefed few major steps for that. The first one is, of course, developing the catalyst at the lab scale. Then there has to be a kinetic model for it. Then we do various testing along with our catalyst partners for long-term testing, stability testing, high-pressure testing, full pellet testing. And then we, based on those data, those model has to be adjusted and updated. Once it's done at the lab scale, the next step is going to pilot scale. And after the pilot scale, the last step to prove the catalyst for the technology is having actual reference at the commercial scale plant. These were all the process that we follow to qualify a catalyst for our technology. There are a few parameters that we look in ammonia cracking catalyst. First one is performance. Of course, it should have a reliable kinetic model. Based on that, we evaluate the performance, and ammonia conversion per pass has to be more than 98 to make it efficient. Ammonia can always be recycled back, but energy efficiency comes into picture. Then next is stability of life. We expect at least 4 years of expected life from the catalyst. So we check for that all the long-term testing and mechanical strength of the catalyst. Then mechanical robustness, I think I covered that. And then cost effectiveness, of course, that is very important to make overall hydrogen cost competitive. Then availability and manufacturing of the catalyst. So the catalyst should be available at the shortest lead time. Having said that, we have gone through these process and confirmed these parameters with different catalyst technology partners. And currently we have established catalyst technology for our S2X technology. And as of today, we are ready to license it and we can license it up to 1,200 MTPD of hydrogen plant. So that's it. Thank you for having the patience to listen to me. And if you have any question, I'll be available. You can reach out to me after this. Thank you.
Thank you, Rajesh and Amit. I think that was a very brilliant presentation. I think technologies like these are what is going to take India to the next level in terms of green ammonia as the sort of revolution picks up. I think the next presenter is from Johnson Matthey. Setu Bajpai is a chemical engineer who's a wealth of experience across clean fuels and hydrogen. She's going to talk to us about refinery assets and how sustainable solutions are implemented there.
Thank you very much. This is Setu Bajpai. I'm Regional Sales Manager for Refineries in India and Southeast Asia at Johnson Matthey. So exciting times for engineers, exciting, a lot of new things happening and a lot of collaboration, some unexpected collaborations also happening in this space. But yes, with a goal, we all have this common goal that we want to have sustainable and cleaner fuel for the future. So Johnson Matthey is very well placed in to support the world refineries and chemical industry to move towards sustainable fuels. As we are seeing there is a transition happening from the traditional feedstocks to the sustainable feedstocks. Johnson Matthey has had a long history of supplying catalyst and technology solutions for the traditional feedstock. Now we also have a lot many technology options, a lot many integration options available in the space of sustainable feedstocks. We do provide catalyst and process technology for this space as well. We have technologies like methanol, formaldehyde, sustainable aviation fuel. So whatever the product mix that you're looking at for a sustainable future, we are in a position to supply both technology and catalyst. So now there's a lot of talk on how we can we can do the carbon reduction, how we can. So there are two pillars of decarbonization. First is the carbon reduction, where we look at the existing assets, what we can do with the existing assets, how can we reduce carbon in the existing chemical units and refineries. The second pillar is carbon replacement, where we are evaluating what to do with all the carbon and hydrogen, the green hydrogen that we are producing. Can this be converted to some any other fuel? How we can replace like all the CO2 that we are capturing? What to do with that? Is the storage only an option, or can we convert it to useful fuels? So Johnson Matthey supports. It's not moving. Yeah. So Johnson Matthey supports these two pillars with these technologies. Under carbon reduction pillar, we offer our technologies and catalysts like Catacell SSR, which can increase the capacity of your SMR just by replacing the catalyst. So it's a very cost efficient solution that we offer. It's a stackable structured catalyst solution that you can put in your existing SMR reformers. We have clean paste technology that combines the autothermal reformers and help you to capture the carbon dioxide from the existing SMRs. We have low carbon hydrogen solutions where we combine our GHR and autothermal reactors, reformers, and help you produce the low carbon hydrogen. Under carbon replacement pillar, we have technologies like JM Hycogen, which can combine your hydrogen and CO2 and help you produce either methanol or methane or like synthetic natural gases. FT-CAN technology, it's based on Fischer-Tropsch reaction, where you can take this hydrogen and carbon dioxide and convert it to synthetic crude oil, and then you can convert it to any fuel like aviation, sustainable aviation fuel, or green diesel, green gasoline, anything. We have also bioforming technologies where you can take sugar-based bio feedstock and convert it to, hydrogenate it to fuel, biodiesel. So I'll talk about the first pillar first. So for carbon reduction, we support it through carbon minimization. This is the Catacell SSR technology. These are a structured catalyst. So generally, like traditionally in SMRs, we have reformers that is loaded with pellets-based catalyst. This Catacell is a structured catalyst. A structured catalyst gives you that advantage that it will definitely improve the pressure drop in your reformers, but it also gives you an advantage on activity. It has a lot more activity, so you can, just by replacing the catalyst, you can actually increase the capacity by 10 to 15%, or you can reduce the carbon intensity by 15%. Instead of pellets, it will be there's a diagram where we have these structured metals that is a tailor-made solution that can be designed for any size of the reformer tubes. And with this structure, we control a lot of flow, how it's happening through the reformer. And the catalyst is coated on these structures. So it's like you will get a step change in performance with this catalyst. The activity is very high compared to the traditional pellet-based catalyst. And it's a very capex wise, it's very light. The payback is very attractive. We have a lot of references for this, and it's a pretty mature technology. Under the carbon reduction pillar, we also have clean paste technology, which actually transfers the CO2 emissions from the fuel side in your traditional SMR to the process side. So you can take the PSA off gases, and it uses an autothermal reforming, burn your flue gases, and you will get CO2 at the high pressure. Then that can be extracted and then used. Whatever you want to do, you can do that. It's a low capex solution. It also offers a benefit, like some of the refineries have many hydrogen units in their facility. So you can have a single system for all those trains, and so it gives you that advantage as well. There's the modularization opportunity, so it saves a lot of space. And we also have a technology for producing low carbon hydrogen. This combines the GHR and ATR technologies. ATR is this also autothermal reformer, where you take feed gas and burn it directly in this autothermal reformer along with oxygen. So like people have been thinking like we are electrolyzing water and producing green hydrogen, but you're also getting a lot of oxygen that is almost free from those electrolysis. So that oxygen can be integrated and used in these autothermal reactors. What happens, this is a very highly efficient reactor. You're not taking your feed and process gas through the tubes, you're directly burning it onto the catalyst. Plus, this is a direct saving on fuel. You do not have to burn fuel in the reformers. You can you're using actually the feed to supply that heat for the reforming process. It is combined with a gas-heated reformer process. Almost 30% of the reforming reaction happens here. So this combined block gives you a very efficient process. It's a very low carbon intensity process. You can capture up to 99% of the CO2 that you're generating. It's a low-cost hydrogen production with lowest capex and highest feedstock efficiency. And this is not a new technology. We have been using these autothermal reformers as a secondary reformer in your ammonia synthesis loop. So we have a vast experience in this. Okay, but no, it's not moving. Okay. There's also a lot of integration possibilities available. So if you are producing low carbon hydrogen, there is a possibility, like if you want to go to the ammonia loop, because people talk about how to, whatever hydrogen you are producing, how to transport it across the globe. There is a possibility that you can integrate an ammonia synthesis loop with this low carbon hydrogen, where you can produce blue hydrogen that can give you blue ammonia through this ammonia synthesis loop. We partner with Uday on this. The LCS technology and catalyst comes from JM. For ammonia synthesis loop, the technology is from Uday, but the catalyst is from Johnson Matthey. This integration offers a high feedstock efficiency for ammonia production. And we have a lot of experience in this, more than 30, 40 years of experience. If you've chosen an ammonia synthesis loop, there's also an option to have an ammonia cracking technology. JM also offers an ammonia cracking technology along with our catalyst. So that can be used for transportation. Now coming to the second pillar, carbon replacement. So there's a lot of carbon capturing happening, and people are now, like in countries like India, where you do not have like you do not have much of the storage space. It becomes very expensive to extract that carbon and like transport it to some other country. So there's also a possibility that you can convert that CO2 to various useful products. We offer technologies like FT cans. Here we partner with BP. This is a Fischer-Tropsch based technology, which is here you can combine this syngas to and convert it to synthetic crude oil. This synthetic crude oil can be cracked, can be processed and converted to any useful product like SAF, biodiesel, green diesel or green gasoline. We also have technology for e-fuels where you can convert, either you can take that Fischer-Tropsch route to, and convert it to synthetic crude, or you can convert it to methanol. Then we also have bioforming technology where we also partner with Virent, which takes in the biomass and hydrogenate it and convert it to biofuels. So talking about Fischer-Tropsch technology, it uses this FT can reactor. It's a tubular reactor, capex light option. We have a proven robust record of 40 years of development and demonstration. FT cans reduce the unit cost by approximately 50%. This high CO2 utilization. There's two options. If you have biomass, you can gasify it, and then the syngas can be taken to this FT cans. Or you can take your green hydrogen and combine it with the extracted CO2 and convert it through our Hycogen process, convert it to syngas. This is where we do the reverse shift reaction and it gets converted to syngas. And then again, it can be taken in FT cans and converted to synthetic fuels. And bioforming process uses this hydrogenation route. It takes sugar-based bio feedstocks, hydrogenate and convert it to bioformates, and then that can be converted to biofuel. So we offer both catalyst and technology for this. We have e-methanol technology. Again, this is so Johnson Matthey is one of the is the leader in methanol licensor. Capacity-wise, the world's largest methanol unit is licensed by Johnson Matthey and uses Johnson Matthey catalyst. So we have a technology that is proven at a scale. So you can take that syngas and process it into methanol converter. And this is the technology called Emerald. So we have a highly stable catalyst that achieves high productivity of methanol over a significantly longer lifetime. Very highly efficient process. You convert hydrogen and carbon dioxide to methanol, and that can be used for blending. Okay, so we also have a route to convert this syngas to synthetic natural gas. We have a process that converts, that uses this methanation technology. We offer both technology and catalyst for this technology. This takes your, if you have a gasifier, any gasifier, a biomass gasifier, a waste gasifier, and if even we also have options, this option can also be used if you have coal gasifiers in your facility. So it can take that syngas, combine it with hydrogen, green hydrogen from the electrolyzers, take captured CO2 if you're taking this route, and methanate it to ESNG. with all these technologies, these are the various references that we have announced recently. A lot of all across the globe, they're using JM technology and catalyst at various capacities. So it's all over the world. So we have proven, we have commercialized operating units for all these technologies. Johnson Matthey can be a bankable strategic partner for our customers. We do recognize that it's a time of collaboration. We are partnering with the best of the companies in the industry, and in order to give you an integrated solution that can help you achieve your sustainability goals. We provide you cost-efficient, proven solutions. There's a lot of technology. Johnson Matthey is an old company. We have more than 75, 80 technologies in our portfolio, and there's a lot of integration possibility that you can look at. We are a very highly reliable technology partner. Just give you a brief about the company. We are a 200-year-old company. We have been a global leader in sustainable technologies. We are a member of the inaugural board of the Hydrogen Council. Johnson Matthey started as a platinum, like a precious metal assayer in UK. And from there, in this 200 years, we have moved from like a recycler in PGMS, and then we have also developed a huge technology and catalyst portfolio that can support both your emissions, automotive emissions, plus can also handle the emissions for the chemical and refineries, chemical industry and refineries. We have more than 480 plus licensed plants over the world, 60 plus years of experience in syngas. And we have been an hydrogen industry leader. So we are very well placed to support you in this market. Thank you.
Thank you, Situ, for that wide selection of technologies that you're offering. I think where the rubber hits the road is when techno-commercial viability comes into question. And I think our next speaker, Shefali from BP, is going to talk to us about hydrogen cost optimization, especially in the refinery context.
So I'm here to talk about an experiment we ran for end use of hydrogen in industry. And what we realized was steel is actually a pretty attractive option for various reasons that my esteemed colleague, Mr. Naveen Alawat, has already mentioned in the previous talk. So in fact, thank you for giving that preamble. Going to the relevance of steel, and I think a lot has been said already, but just to add to what's been said, steel is not just 1% of world's GDP, it enables another 3x of world's GDP. And it directly or indirectly supports 100 million jobs, 100 million households. It is important to the world for grow and survive. It is extremely important for the world to have steel if it is to meet its Paris goals, because nothing in new energy business or even the traditional energy business is possible without steel. So decarbonization or energy transition in steel is an imperative. And it's not easy. It's already been mentioned. It is a hard-to-abate sector. And it is estimated that about $3.5 to $5 trillion will be needed to decarbonize it. But a smaller proportion of that capex is expected to be in steel industry itself. A very large proportion, something like $3.5 trillion, is expected to be brought in by the energy businesses to decarbonize steel. It's the energy decarbonization that leads to decarbonization of steel. And that's what really makes steel industry and energy industry almost need to work together as partners and as collaborators to make this happen with the help of all of the other ecosystem service providers, component providers, technology providers, which are on the dais today. Just for reference, for those who are unfamiliar how steel is made. Steel is essentially a three-step process. First is material preparation, which has some energy use. It is some carbon emission. Second is that iron ore that has been prepared is then put into a furnace and reduced to iron using a reductant called coal, largely in the world today, which is the BF-BOF process, or gas, which is also fossil. So carbon is the primary reductant that is used today to convert iron ore to iron. And then iron is converted to steel, believe it or not, by alloying it with carbon. So there is about 2% carbon mixed back into iron ore to make it steel. And between these three large steps of making crude steel, which then subsequently goes into castings and finishing, etc., the steel making, the bulk of the emissions reside in the iron making process. And this is where the lies the rub. Iron making is such a large operation and such a reductant heavy operation that substituting it with any other reductant is usually a challenge. Now there are two major processes that currently exist in the world to make steel. The most prevalent one is BF-BOF. Hydrogen can be used in BF-BOFs. There are experiments, there are demonstration scale plants that are coming up now, and we don't know the end game or end state of this particular experiment, but there are various technology players and operators looking into this problem. However, for the purpose of the presentation today, I will be probably talking a little more about the DR process, which is the other process, less prevalent, based on gas, fundamentally different from BF-BOF, but it is more amenable to using hydrogen going forward. And that process is something that we keep talking about to say, yes, the entire steel industry needs to move out of BF-BOF, probably go to DRI type processes, so it can use more natural gas, more hydrogen, which are cleaner fuels, and therefore decarbonize or take the steel industry to an energy transition. However, there is no one solution. Every solution is needed in conjunction with each other, including also traditional energy formats and forms to really decarbonize steel. And when we talk about decarbonizing steel, we've already discussed recycling and usage of scrap. We've already discussed being as efficient as you can in your existing processes. But the three breakthrough technologies that are mostly talked about need to work in tandem for decarbonization of steel. One is CCS, capture the carbon, store it. Not every current manufacturing facility of steel has access to a carbon store. Capturing carbon in an existing steel facility is also a challenge because of space and other constraints. Hydrogen, use of hydrogen. Hydrogen is very costly, very hard to transport, very hard to store. And process electrification, the new kid on the block, where it's expected that one will make steel or rather reduce iron much like how you reduce aluminum. Put it in an electric arc furnace and then basically split the iron ore atom into iron and oxygen. So that is also a new technology, yet to see traction. We are looking at lab experiments today, and maybe it will take off, maybe not. But what's available today for pretty much everybody to use is hydrogen, and especially if the equipment happens to be a DRI plant. And what are its advantages? One, usage of hydrogen in an existing DRI plant or even a new greenfield DRI plant, the steel is as good, if not better. Most of the time, the challenge has been, if you don't have a BF type operation, then how do you do a process which needs very high level of purification, and a steel process which is needs high level of purification, and a DR process cannot do that. Well, as long as you're using reasonable quality of iron ore, steel is as good, if not better. There is no change required except for maybe minor retrofits, and if you're building a greenfield DR plant, no change required in process to include hydrogen in it. The challenges, as I said before, are basically hydrogen making is capex intensive, even more so than steel capex. The biggest hydrogen stacks of technology that are available today can service only a fraction of steel making. So the standard equipment size of steel making unit in DRI is what, 1.5 million tons, 2 million tons. A steel stack, a hydrogen stack can service maybe about 20 to 30% of it reasonably well. to get to 100% hydrogen induction into in a DRI, in a standard DRI furnace is some years out. The hydrogen making technology has to do a bit of catch up to get to that point. However, that shouldn't stop us from start including hydrogen in our current fuel mix, mixing it or blending it with gas and looking at its use cases. And one such use case is to put it in a DRI furnace. And that is what I will demonstrate in my next slide. So how did we develop an end use case? First, we looked at all of the systems of hydrogen production and steel production. And we realized that if you co-locate or synchronize the two systems, there are significant cost savings. The cost savings reside on the hydrogen capex side. There is the obvious one, right? Reduction in transportation cost, use of oxygen that has been spoken about in the same system. But there are others. For example, power balancing. Because both steel and hydrogen are power intensive, you can do better power balancing by synchronizing the two systems. There are efficiencies in water users. You're splitting water on one side and combining water on the other. There are synergies on water usage where probably if you're sitting near a sea, you don't have access to water, you're putting up a desal plant. To set up a hydrogen plant, steel can actually solve that problem. Also, it allows us, if you're optimizing the two subsystems of power generation, hydrogen generation, and steel making together, then there's also an opportunity to do very efficient management of both electrical storage, any kind of intermittency management for power, whether it's a gas turbine or whether it's a grid, and or hydrogen storage as well. And that, small incremental changes or management of that system brings incremental savings, and the combined weight of those incremental savings is actually significant. And that's the discovery we made when we did this experiment. So what we did was really we evaluated a live site, potentially a greenfield DRI plant in a location where we had the information for. We broke up all of the subsystems first, did a theoretical exercise on understanding the interrelationship between each of the subsystems in steel making and hydrogen making together. Then we isolated the systems which had the highest impact on hydrogen costs and therefore production of iron costs. Those systems were then taken back into an optimizer and optimized further. And I'll touch upon how we optimized it going forward. But basically, the idea was to look at the most important subsystems, optimize them together, irrespective of whether they sit in the steel making battery limit or hydrogen making battery limit, because usually these are treated as two separate fences. Hydrogen is one side of the battery, iron and steel is another side. The two systems don't talk to each other very often. We tried to make them talk to each other, and this is what we got. So in the process of optimization, we matched every subsystem capacity to ramp up, ramp down, the flexibility back into the use case system. We also put in all the flexibility parameters of the electrolyzer, of the power generation plant, the flexibility parameters of the DRI plant, and potentially there is an addition coming, which is the AF plant, to look at power, temperature, water, hydrogen, and other gases together. And what that yields, and obviously there are some immutables there, some things you can't overcome like physics and chemistry, but whatever is the immutable was put into the optimizer, whatever was flexible was also included in the optimizer. And once we ran the system, when we ran the multi-system optimizer using dynamic modeling to get to a system optimum. What is a system optimum to produce iron from this system? And in that system optimum, we ran multiple scenarios and systematically we were able to reduce our total capex of the various subsystems. At a collective level, our LCOH, which is cost of producing hydrogen, came down by 30% from the original baseline. And at a HBI, cost of resultant iron that was produced was also down by 32% from the original baseline. So that just basically tells us that there is, by working and collaborating together, there is actually a lot of synergy, a lot of cost saving, and a lot of optimal operations that are possible. It's just a matter of being transparent and working in the spirit of partnership with each other that can lead us very significantly and clearly into reducing the carbon emissions of hard to abate sector. Next up in some of this optimizers, we are trying to see more fuel blends. So with this experiment was done with a 30% annualized hydrogen blend into a DRI furnace. We're looking at, okay, what if you do 15, where does that take you? What if you did 50, what will that mean, etc. So there are various scenarios that are being tested. More modules will get added going forward in this optimizer. But at the first level, it's a very encouraging option to say, if you're faced with anything which is intermittent on one side and needs to be consistent on the other side, every system has an inherent flexibility, small. Add up all of the small flexibilities by optimizing systems together, the production systems and the end use systems together, to bring down the overall cost of the system and the resultant product. So what we learned is that there is merit. The time and effort that we spent in doing it was well worth the while given the results we got. It needs a sophisticated toolkit, and companies like BP do have this, to the ability to simulate very large amounts of data and very large amounts of parameters on a single platform. But doing this as purely as a theoretical exercise does not work. We had the benefit of a equipment supplier and operator in the mix who was advising us when we were building the simulator, and potentially it's operating in such a way that it can be reverse engineered for any target variable. So our target variable was lowest cost of hydrogen production, but the target variable could very well be lowest cost of HBI production or steel production eventually when the full module is built. And can be tested further with other parameters that we probably don't even know anything about and depend on the steel producers to give us. So that's really what we learned, and I encourage all of you to kind of look into your own industry to see where multi-system optimization is possible, and reap the benefits of what's available when you're looking at intermittent generation systems and new energies and consistent traditional systems of making something like steel or cement or ammonia. With that, thank you very much. I'm available in BP Hall 1B21 for any further questions. Thank you.
Thank you, Shefali, for that. I think it was a very good example of how simulation can lead to lower techno-commercial parameters, especially the levelized cost of hydrogen. I think from a simulation to a live example, I'll call upon Srikanth from HPCL to talk about how they've actually done this in the HPCL Vizag refinery.
Good afternoon, everyone. My earlier speakers have already established the need and the requirement for adopting the sustainable technologies and green hydrogen in particular. I'll be taking you forward through the challenges and the limitations that we have faced in implementing one of the India's first electrolyzer in a refinery. The agenda is, I'll just touch upon what green hydrogen, background, how we, what are the requirements or what are the basis for selection of a technology, how we proceeded for the tendering process, various challenges we have faced and the current status. It is worth to mention that though electrolyzers have been up and running for quite a number of years, in various maybe industries, other industries, or in the pilot scale or in the laboratories, it is important to note altogether that to run to set up and run an electrolyzer in a refinery is altogether a different game because of the safety involvement, quality requirement of the hydrogen, safety aspects involved in it, and already limited space or limited many of the constraints available in the current refinery configuration. And HPCL, just to brief upon, has a legacy of more than 100 years, is one of the largest OMC and had been awarded Maharatna status in 2019. Most of us know this, but just to touch upon, green hydrogen is hydrogen produced by electrolysis using, generally by electrolysis using renewable power, whereas the traditional SMR gasification of methane or the coal, we call it as a gray hydrogen, and when we adopt carbon capture technologies, we are calling it as a blue hydrogen. And background, as we have already touched up, SMR, steam methane reforming, is one of the highest carbon dioxide producing emission sources in the refinery, because hydrogen is required in almost all the steps in which refinery uses for hydroprocessing or desulfurization. So hydrogen is very important, and generally adopted SMR is one of the carbon intensive process. And HPCL has committed for a net zero emission by the year 2040. And in this journey, we have started, or we have implemented one 370 tons per annum electrolyzer unit in Vishak refinery, which was up and running. The capacity, brief details about the project is a 370 TPA hydrogen, uses a single stack 2.6 megawatt. Water capacity used was 0.5 meter cube, is an alkaline electrolyzer with the aqueous KOH solution is the electrolyzer, and our EPCC partner is Technip Energies. Just to touch upon what is the basic difference between our various technologies, at least that are available at a commercial scale and easily adaptable, where alkaline electrolyzer and the PEM. Basic difference is how our OH, what passes through the membrane. If an OH ion passes, it is generally an alkaline electrolyzer, and if H plus ion passes, it is a PEM. And this was the brief process about the electrolyzer. We know that green hydrogen production has electrolyzer at its heart, and the KOH or any electrolyte is continuously passed through the electrolyzer, where hydrogen and oxygen are produced at a respective anodes. And these mix of oxygen and the KOH solution passes to an O2 tower, where the solution separates and the oxygen is cooled, and after moisture separator either can be used to its destiny or it is vented. Similarly, in the case of the hydrogen, it passes through a hydrogen tower, where the hydrogen and the KOH or the electrolyte solution separates. Hydrogen gets cooled, passes through a moisture separator, and is further processed in hydrogen purification steps, because there is always oxygen which is unwanted, which can damage the downstream catalyst. So purification is essential, and to make up or to maintain the level wherever, because water is the raw material here, and DM water is being added upon to continuously make up or to maintain the level. This is the basic steps of once hydrogen is generated from the electrolyzer, it passes through a deoxy column, where a platinum or a palladium based catalyst converts the remaining oxygen into the water, separates it in a deoxo cooler and moisture separator, passes through a series of adsorbent beds, so that we get highly purified hydrogen that can be used in the downstream process. Various catalysts normally used was deoxy catalyst, molecular sieve for hydrogen drying, and we have a chiller system which uses environment friendly reagent. And just to touch upon the point, green hydrogen is really green because we don't have any solid effluents, and gaseous effluents is oxygen that can be used or vented to the atmosphere without any harm. And hydrogen venting will be required during the startup when it was impure, and liquid effluents were mostly water and the chilled water drain, and KOH electrolyte during the replacement. And coming to the selection of the technology, so we have already discussed, or various speakers have already discussed this topic in wide variety. I'll just touch upon the context in which, in a refinery context. So hydrogen, as indicated earlier, is very much used in hydroprocessing units, and the quality is of very utmost important, because it impacts catalyst life, catalyst poison may happen, product quality will be impacted, and the compressor compatibility also may come into a question. So that is the reason complete details into how a technology works needs to be established before adopting in a real case scenario. Similarly, coming to the specific case of the VR has gone, Vishak refinery has gone multiple expansions, and this And this is where the current plot limitations come. We don't have the ample space so that we can experiment, or we can have a large space for the adoption. Similarly, because it is a real life implementation, the capital cost is very important. Capital cost not at a starting initial year, but because the stacks and stacks and the cells have a life of a few years, they undergo a specific replacement every other 5 or 7 years based on the suppliers. So this cost is also to be factored in before choosing on the technology, because maybe at the starting point, at the point 0, it may be cheaper, but in the run life, it may become as a costlier option. So we need to evaluate before adopting a selection, a particular technology, where and how this each technology stands at. And this was the process in which we have selected one of the finalized on the who is going to supply us this electrolyzer. In any general case PSU tender, it is a proven track record. That means we already need to, everyone needs to establish or show us that we have already implemented this solution, so and so, and you can also adopt it, this. But in this specific case, it is not possible, because it's going to be at this scale, at about 2.6 megawatt, we don't have any Indian refineries, or at least a model running in the in a refinery. So what we have, based on multiple discussions with the various partners, a revised methodology was followed, where a DJU, deed of joint understanding, along with the electrolyzer manufacturing with the EPC bidders. This format is also allowed along with the traditional approach. And evaluation, as I have discussed earlier, it is not just the initial capex that needs to be considered. We also need to consider the OPEX part, and also the periodical replacement of the stacks that are going to happen in a lifespan. Suppose each unit typically in a refinery operates for 20 to 25 years. So this calls for at least 3 to 4 times replacement of at least electrolyzer stacks. So all these costs, and when we come across various vendors, each one will be supplying with a different part of hydrogen purification system. Some offers one catalyst, some offers other catalyst, and even the electrolytes, even everything changes. So how to make everyone on a similar scale? So we adopted an NPV basis, where all the costs, including water consumption, electricity consumption, what is your caustic requirement, everything was sought, and all these were even the life of the stack, the cost of this stack only in the total, along with the BOP, have been taken into consideration in arriving on a net positive net present value, and this is the basis in which final contract was awarded to the bidder who has obtained the maximum NPV. And this was an electrolyzer system model, 3D model, where this was the basic stack, a rectifier, PLC controller room, and this was the purification system. Stack container and the purification container. And just to touch upon few challenges, as I have already explained or touched upon, limited technology providers and their execution in the refinery, because refinery we have many regulations and many certificates are required for each and everything. It starts with the area classification, hazardous area classification, and most of the vendors, though they have supplied parts in pieces and to the other industries, the refinery requirements, where everything needs to go through a piece of clearance, is altogether different. So that was one of the first challenge. And by the time when we are implementing, there is no firm statutory guidelines also which standard is to be followed. And there was a difficulty in finalizing the design drawing, because generally we can refer to the already established unit if it is available, but in this case we don't have. Another challenge in a refinery is, as already said, hydrogen is impure, or during the startup and shutdown may not meet the quality standards, and it has an impurity in the form of the oxygen. And what to do with this hydrogen mixed with the oxygen. What to do? This was one of the challenges. And the complex scope with multiple interrelated components is always a challenge. And containerized approach that which we have chosen has some benefits, and it also has a challenge in the form of execution and maintenance, because everything comes in a small bit of piece, and if we want to do maintenance or if we want to do a replacement, it's going to take a longer time, and it's going to do a lot of challenge. And area requirement, though initially we say plot requirement is one of the challenge, but because impure hydrogen needs to be vented. So when something needs to be vented, then there in safe area has to be earmarked around that vent, and this itself requires a lot of plot area, and this was one of the challenge. And as said, because in this field expertise is very limited, and even the vendors has to depend upon only one or two few experts in this field, and this is always a challenge in the execution timelines. And the current status, first to have the challenge of venting hydrogen, a dispersion study has been carried out to identify at what height, if this impure hydrogen has been vented, then it doesn't create a flammable mixture. And finally, venting was chosen, and then a series of safety steps like a pre-commissioning safety audit was completed, OST audit was already completed, PESO clearance was also obtained, and this green hydrogen plant was commissioned. And this was the plant in which we are speaking, real plant. This was a transformer bay, this was the electrolyzer, this was the purification system. And finally, just to summarize what I have already presented, the major challenges in a refinery scale implementation is the plot requirement and the initial capital investments, and those, how do we calculate, or on what do we consider as a capital investment, is something that needs to be taken into the account. What we have to have wider participation, we have allowed EPC bidders along with the DGU, a new methodology that has been adopted so that more and more bidders can participate. And other things that we need to note, it's not only when in a real life situation, it's not just electrolyzer system and its design. Lot of balance of plant activities like hydrogen purification system, your DM water quality, DM water availability, and other utilities, and the electrical part of it, the substation, the rectifier system, all these are also an important part of the electrolyzer system which needs to be focused upon while implementing a real life situation. And we need to closely follow the statutory approvals for the green hydrogen production, because they are being firmed up and are being released. And this presentation is for sharing our key learnings and experiences so that it will be useful for everyone. Thank you.
Thank you, Shrikant, for that. I think that's fantastic to see a live example, right? And I think my big takeaway from this session is that all the speakers have echoed that there needs to be collaboration across industry players, across technology providers, and that's something I see, very encouraging for even us consultants like it. So that brings us to the end of this session on hydrogen end use. A big thank you to all my speakers for sharing their valuable insights, to the organizers for putting together such a wonderful session, and to you, the audience, for being such patient listeners. Thank you, everyone.